Hey, what's up, guys? Okay, so this is my another video about this BQP and BPP. Okay, so this video I want to talk about some so-called mathematics between the quantum supremacy. So basically, I want to talk about quantum supremacy like in more like high level way, or why people believe that that this BQP should be different from BPP, or at least the sampling version. Okay, is a sampling version of BPP is different from BQP is different from BPP. Okay, in order to do this, we need to I think everybody knows that you can check out my other videos, but there's an idea called polynomial hierarchy. So basically, you can define a polynomial hierarchy to be like you start from P, and you start from P, right? And you can define NP. So the definition of P just there's a polynomial term, there's a Turing machine that you can solve in the polynomial time, right? And NP means that there is a polynomial verification. So basically, there is a polynomial verification for given x. If x belongs to L, right? So for there's a y which is polylength of x, and the poly Turing machine that Turing machine that run vxy and output one, and you can define NP to NP. Basically, ask you can define this NP to NP to be the SS of oracle of NP. Then you can define NP to NP to NP, and then this is the same as you add more quantifier, and you can define polynomial hierarchy to be all this class. Okay, with yeah, so this is a union, the union of this. So any problem in the polynomial hierarchy basically means that it belongs to one level. Okay. Okay, so okay, and the belief, the much more the deep belief is that this pH will never collapse. Okay, so this means that there is a no so usually people can draw this as this way, right? You can have NP and a co-NP, and you have the sigma 2 and the pi 2, sigma 3 and pi 3, and keep going. Okay, so pH never collapse means that there is no such level that two of it will be the same. Okay, so and then there is a fact which is a Toda theorem. Very difficult to prove. Basically, P to a sharp P is contain pH. So P to a sharp P basically it's all it's the simple speaking is that let me just think say it very informal. So basically it's that given Boolean function. Okay, so given the Boolean function, let's say the n variable, and the sharp P need to output. So when I say so this sharp P machine need to output a counting of both the number of solutions, so counting the number of solutions, such that fx1 xn equals to 1. So sharp P is a difficult task, right? You ask all the solution, not ask all the solution, but ask how many of solutions. Okay, and you can define an ideal coparity P. Basically, it's it counts the number of the number of solutions even or odd. Okay, now you can also define the like more abstract object called the mod PP. Very bad notation, so let's call it mod KP. Basically, it counts that number of solution, whether the number of solution is divisible by P. Okay, so basically these are so-called counting class because it related to the counting of the solution. Okay, and the non-trivial proof is that very non-trivial. This is the Turing awards results. Basically, is that the polynomial hierarchy is basically in this P to a sharp P if you have access to this sharp P oracle. And also you can prove that pH is in a BPP to a parity P. So if you have that randomized algorithm that with this is parity P, which is very powerful, that you can get all the hierarchy. Okay. Okay, so but there is another class called GapP. Okay, so GapP is also weird. So let me just write in this way. Okay, so this is the what story comes from. Okay, so one can define an idea called sharp P, and also there's an idea called GapP. Okay, so simply speaking is that as I say, right? So let's imagine. So one can reference the Sharpie to be like, say, you have some Boolean function, and then you want to output 1 divided by 2 to the n summation of f of x. Right? You want to count the number of solutions, and this GapP is defined to be if you have Boolean function, but the domain is like -1 to 1, and then you want to count you want to sum of the. Also, you want to ask the sum of all these f of x. Okay, and yeah, it's just output. Okay, so right, so these are like two different things. Okay, so it looks different, but this is non-trivial whether they are really different. Okay, so why these two are very important? Because in this one, basically the difference between these two give you the difference between the quantum and classical. So for the Sharpie, that you can, yeah, basically if you ask, right, if you start with any like BQP, right, given that you can check that if you can prove that if you can solve the Sharpie problem, then you can exactly compute the probability of the classical randomized machine output. So only randomized machine, randomized algorithm. You can compute the probability of randomized classical algorithm, the accepted probability by the Sharpie, because you can just count the number of accepting paths, right? So basically, you just count the number of accepting paths. Okay, and the 2 to n is just some factor, right? So this n is just basically, in this case, it's the internal randomness, right? Suppose, so if you throw dice, then the paths will separate once, and you throw dice 2, that's 2. If you throw dice 2 twice, then this computational path will spread into 4. Okay, and for the GapP, that interesting is that this is basically the quantum. Okay, so let me just tell you the why, because if you start from 0 to n, and then you go to hard mod, and then you go to the QRF. So this QRF map x to f of x. So this is the computational model, and then go h, right, and you measure all this 0. Okay, so after this, the state will be this, and after f, the state will be this. Okay, and after hard mod again, the state will be 1 over 2 to n minus 1 x y f of x y. Okay, so if you measure y to be 0, you ask the probability of this guy accept output of 0. So basically, y 0 0 0 0 is basically what? You can easily see that this is just, you put y equals 0, so you get this. Right? So you get, because y 0, right? So you get f of x, sum of x, and then square it. Okay, so basically the probability of this quantum, if you can access this quantum computer, then you can compute this GapP. Okay, and yeah, so this is the first thing. Okay, so one is the classical, one is the quantum. If you want to say this, one is Sharpie, one is GapP. Okay, so very interesting is the following. So first one is that actually P to a Sharpie is the same as P to a GapP. Okay, so this is weird, right? Because this tell you that one can compute, if one can compute Sharpie exactly, then one can compute GapP exactly. So one can compute Sharpie and GapP by each other. So if you have Oracle to compute the Sharpie, then you have the Oracle to compute GapP. If you have Oracle to compute GapP, then you have Oracle to compute Sharpie. Okay, and so this is the proof. Basically, is very simple. So let's maybe go one directions. So suppose I have a function, right? I can go to this. I have this, So this direction means that if I have this sharp-p, I want to calculate GapP. Okay, so if someone hand on this GapP function to me, then I can say that, oh, it's very trivial. I define a G to be f plus 1. Basically, it means that I define 0, 1 to n to be 0, 2. Okay, then I just put G into my my sharp-p oracle. Okay, so this tell me that I need to divide it by 2, right? So I just put G divided by 2 in my sharp-p oracle. So my sharp-p oracle will output this, right? Will output this for me. And but this is trivial, right? It's basically f of x plus 1 divided by 2. Okay, so equal to something. So I can calculate the sigma summation of f of the original GapP, the GapP function that I want to compute. And then conversely is also the same thing, right? So if somebody hand in the sharp-p function to me, then I can just move into GapP function by just for this 0, 0, right? Just add another task, add another register to be the -1. Okay, so I just automatically modify this 0 to 1, to -1. Okay, so if I start from this sharp-p, the sharp-p function, then I can define a G to be 1 if fx output 1. If fx is 0, then I hit G -1. Okay, then I just compute G, right? Because I have the now I have the GapP oracle. So you just use GapP oracle. So this GapP oracle will give you summation of G of x, right? Basically, it's the accepting pass minus the rejecting pass. Okay, but then right, but you know the accepting pass plus rejecting pass is basically 2 to 8. Okay, so you can solve A and R, and then just output accepting pass, right? So just this. Okay, so yeah, so sigma A is just summation of f of x, right? Just the one part. Okay. So this looks really weird that because in the exact case that everybody looks the same, right? Even like this quantum and classical in the sharp-p and GapP looks the same. But the non-trivial part is the approximation. Okay, so here has the non-trivial 2 ingredient. Okay, the first ingredient is that in the approximately, so basically this is a fact, approximately sharp-p function. What constant, right? Say, so basically approximate sharp-p function basically is that means that if there is a c greater than 0, if there, let me just write it this way. Approximate sharp-p function is in BQP to NP. So this is due to the Stockmayer approximate counting, which is a little bit non-trivial. So I will spend the future to talk about this. But approximate sharp-p function is in BQP to NP. So this means that so this idea basically say that there is a BQP to NP algorithm, which output a C approximation multiplicatively. So C is a some guy which is greater than 0. So this means that you can output the oracle. Let's say this algorithm O will output results, and this results in the 1 plus C summation f of x, and also like, yeah, I think it's 1 let's see, yeah, so it should be 1 plus 1 over C summation of f of x. Okay, so basically you will output the multiplicatively approximation of sigma f, and then this is in the BQP to NP. So although compute this guy is very difficult, but output the approximation of this c greater than 0 is non-trivial. For fixed c is in BQP to NP, and then you can using the arrow amplification. Okay, this arrow amplification is also very interesting, but I will talk about future. Basically, you can prove that given any polynomial g, so let's say g is one polynomial n, and then you can prove that this is just this. Okay, so also you prove this just using the amplification. Just compute this. Just start to using this star mirror approximate counting idea that you can prove this. Given any polynomial g, that you can also prove this. Okay, so that means that if I want to approximate this guy, then I can do it in the BQP to the P. Okay, how about this? Right, so we want to know how to approximate the GapP function. Okay, and the very non-trivial thing, very non-trivially, probably not so non-trivial, but very non-trivial, I think, is that the approximate GapP function is still GapP hard. This means that if I want to approximate, if I want to do the previous thing, I want to approximate the GapP function. I want to say that I want to have an output O such that I do this thing. I want to this thing. This guy is the same as is GapP hard. This is almost the same as. Or one can build reduction if there's an oracle O that you can compute this. Then basically you can compute this. Okay, and the reason basically is that because the reason basically is that this oracle will tell you the sign. Okay, will tell you the sign of sigma f, right? So you can just padding with the 0, padding with the 0. So padding with 0 means basically you add a lot of input such that all this input to be correct, and you can just shift. Right? You can just shift the sign. So you can just check when sign change, check where is the sign change. Then you can just do this using binary search. I just forget how to write search. Sorry about this. Okay, so you can use a binary search and then sign changes. Okay, so that means that you can prove that approximate GapP is still GapP hard. Okay, so that means here is GapP hard. Okay, so this tells you that we don't expect, right? So that means that we don't expect that one can basically you don't expect that these two are the same, right? Because so we don't expect approximate Sharpie is the same hardness as approximate GapP. Right. The problem is that if these two are true, if this is true, then BQP to NP will be the P to GapP. Right, but P to GapP is basically P to Sharpie, then basically it's PH, and the BQP to the NP is basically in the sigma 3 because BQP is in the sigma 2. You can check out my other videos to see the proof, but BQP is in a sigma 2. Okay, then so PH collapses into a third label if these two are the same. Okay, so this gives you the results that in the quantum computing that why people believe that sampling BQP is different from sampling BQP. Okay, so start from this, then one can immediately prove. So one can show, one can prove the following. So exact sampling BQP, or the exactly sampling quantum computing is different from the exactly sampling classical computing. Okay, the reason is basically as I said, right? Because you can prove that exactly sampling BQP will be in the P to the BQP to NP, right? And then this guy will be P to a sharp P. Okay, so you can prove this. And the proof idea, basically you start with some quantum. You imagine there is a classical algorithm. So let's highlight the proof. So suppose there is a classical algorithm. I should randomize classical algorithm that the sample that exactly sample the BQP some corner circuit sample all corner circuit. So this corner circuit basically is polynomial gate, and the input is polynomial qubit, all corner circuit. Okay, then what? Then you get a contradiction, right? Because if you can have the randomized classical algorithm that exactly sample all the corner circuit, then basically you can change this sample into counting. Okay, so you get BPP to NP with this sample algorithm. Oh, here. Okay, and this guy is classical. And then since if you run in polynomial times, then you don't care about this. Oh, right? You can just forget about this. But this guy will be it's the P to a GapP. Okay, so you will get contradiction. If polynomial hierarchy never collapse. Okay, so this tell you that this theorem, the assumption is that if pH never collapses, then exactly sample BQP is different from exactly sampling BBP. And the reason comes from this GapP and approximate counting. So these two ingredients that I haven't spent time in this video, but I will spend time in the other videos. See you guys next videos.